Good morning. Today we will discuss about the hysteresis motors. This is lecture number 6. Contents of the presentation: hysteresis motors, its construction, principle of operation, performance, torque, development, torque speed characteristic, advantages, disadvantages, and applications of hysteresis motor. Hysteresis motor. Hysteresis motors are synchronous motors and may be operated by single phase or three phase supply. This motor operates at constant synchronous speed or at no speed, means either it will operate at synchronous speed, otherwise it will not operate. It has uniform air gap with a smooth rotor and uses no DC excitation. As shown in this figure, the outer frame of the motor has a stator and the inner part is the rotor of the motor. The outer frame has slots similar to a single phase induction motor, and it is having two windings, auxiliary winding and main winding, exactly similar to a single phase induction motor. And it is a split phase motor using capacitor also. So the stator is shown, its shaft is shown, rotor of chrome steel and air gap. This motor has uniform air gap and rotor is a perfectly smooth cylinder. Rotor is having some chrome steel material for the magnetic material outside the shaft of the rotor, or it can be a ring over the rotor, outer ring of the rotor. The torque is produced due to hysteresis and eddy currents induced in the rotor magnetic material by the rotating flux produced by the stator. This is one more pictorial view of the motor in which air gap is shown, aluminum rotor is shown, and hysteresis rotor ring is shown, which is at the outside of the shaft. Stator main winding and auxiliary windings are also shown. Stator construction. The stator of a hysteresis motor is similar to an induction motor to produce rotating magnetic field. Means the stator windings are so wound that they can produce the rotating magnetic field. Therefore, the stator of this motor can be wound for single phase or three phase AC supply. So, rotating magnetic field is to be produced whether it is a single phase motor or it is a three phase motor. For a single phase small size hysteresis motor, the stator can use permanent split capacitor type or shaded pole type windings. The capacitor is used in auxiliary winding to produce almost uniform field. This diagram also shows the rotor, hysteresis rotor, which is a smooth cylindrical rotor, and the stator is shown on the right side, which is having two windings, main winding and auxiliary winding. This stator is exactly similar to an induction motor, single phase induction motor. Rotor construction. The rotor of a hysteresis motor consists of aluminum or some other non-magnetic material. In some motors, a solid ring may be used. In small motors, a solid ring may be used, but in large size, the outer layer of rotor has a number of thin rings or thin ring type laminations. Means the rotor is to be laminated. Outer ring of the rotor is to be laminated. The outer rotor ring is made of special magnetic materials like hard chrome or cobalt steel having very large hysteresis loop. If hysteresis loop area is large, it means the hysteresis loss will be large, and because of the hysteresis loss, the torque is produced in this motor. That's why the large area hysteresis loop is required. The rotor is a smooth cylinder and does not carry any winding. In previous diagram and in this diagram also, it is very clear that the rotor does not have any winding, or it is not using any rotor bars. It is just a smooth cylindrical rotor. So special magnetic material is used as a outer ring of the rotor, that is called hysteresis ring. It is shown in blue color in this diagram. And non-magnetic material, rotor is made of non-magnetic material like aluminium, which is shown as a hatching, red color hatching in this rotor before the hysteresis ring, inside the hysteresis ring, and at the center there is shaft. Motor operation. When single phase or three phase supply is given to the stator, a rotating magnetic field is produced. This field of stator magnetizes the rotor ring and creates pole on it. Means poles are created on the rotor and equal to the number of stator poles. It means the stator poles creates equal number of rotor poles. The induced rotor flux changes its direction or field axis due to the high hysteresis value of magnetic ring of the rotor. As the rotor has high hysteresis value, because of that the flux entering from stator to the rotor through the air gap changes its direction basically. So the axis of the stator field and axis of the rotor field are shifted basically, and there is an angle between these two. So the magnetic field in a hysteresis motor, how it is developing the torque. The induced rotor flux lags behind the rotating stator flux because of the higher hysteresis loss in the rotor. The angle delta between the stator magnetic field Bs and rotor magnetic field Br is responsible for the production of torque. So this angle between the axis of two fields, stator field and rotor field, is only responsible for the development of torque, and this torque does not depend upon the frequency. In this diagram clearly the vertical axis of the is of the stator field, and delta angle shifted axis is of the rotor field. Stator, rotor, and the flux passing through the stator and rotor is shown in this diagram. The rotor field, the angle delta depends only on the shape of the hysteresis loop of the material, rotor magnetic material, and not on the supply frequency. So this delta angle is independent of supply frequency. Therefore, a magnetic material having a wider hysteresis loop should be used for rotor magnetic ring. Thus, the coercive force Hc and the residual flux density Br of the magnetic material should be large. As shown in this diagram, the vertical component of this BH curve from the center is the residual magnetism. Means during magnetization and demagnetization there persists some flux or magnetization or flux density, that is called residual magnetism. An ideal material would have a rectangular hysteresis loop. The ideal material for the rotor of hysteresis motor should have a rectangular hysteresis loop. Cobalt vanadium type materials are used in hysteresis motors as they have very wide hysteresis loop as shown in this diagram. So this is the hysteresis loop for rotor material. Some more BH curve or hysteresis loops are shown here. The smaller loop area and smaller coercive force is there in this first soft magnetic material. So in first figure first, this is for soft magnetic material. So coercive force is small. In the figure 2, it is for hard magnetic material. It is having large coercive force, means the BH curve area is larger. It is almost rectangular. So it is having large coercive force. Coercive force is basically the horizontal width of this hysteresis loop or BH curve. Torque production in hysteresis motors. The stator magnetic field produces eddy currents in the rotor. These eddy currents produce their own magnetic field. Thus, there is an additional torque acting on the rotor due to these eddy currents, and that the eddy current loss is given by PE is equal to KE F2 square B square. Here KE is a constant and B is the flux density. the eddy current frequency F2. The eddy current frequency, that is the induced current in the rotor. So it is the rotor frequency F2 is SF1, where S is the slip and F1 is the supply or the stator input frequency. Then eddy current power loss can be modified by putting the value of F2, PE is equal to KE SF1 square B square. The eddy current torque is given by TE is equal to PE upon S omega S, that is equal to K1 into S, where K1 is equal to KE into F1 square B square upon omega S. Omega is the synchronous angular speed. Eddy current torque. The eddy current torque is proportional to slip and it is maximum at starting of motor. From the previous equation we have seen that torque TE is proportional to slip. So the eddy current torque is proportional to slip and it is maximum at the time of starting of the motor as slip is 1. As the motor speed increases, TE decreases with the slip and vanishes at synchronous speed when slip is 0, because at synchronous speed slip becomes 0, so TE will also be 0. The torque TE helps in the starting of the motor. The stator current falls off and the rotor acts like a permanent magnet as residual flux is developed on the rotor. The machine runs as a permanent magnet motor at synchronous speed. So because of the large size rectangular shape BH curve or hysteresis loop of the magnetic material of the rotor, the residual flux persists there, so it becomes like a permanent magnet. Hysteresis torque. The hysteresis loss in the motor is, or the rotor of the motor is given by PH is equal to KHF2 B raised to 1.6 is equal to KH into SF1 by putting the value of F2, KHSF1 B raised to 1.6. So hysteresis torque is given by TH is equal to PH upon S omega S is equal to KHSF1 B raised to 1.6 upon S omega S, that is equal to K2. Means S is cancelled from numerator and denominator, so all remaining parameters are constant. So torque, hysteresis torque is a constant. The electromagnetic torque developed due to hysteresis is plotted with the speed in the figure shown in this on this slide. The torque TH remains constant at all speeds until the breakdown torque. The TE any eddy current torque is 0 at synchronous speed, and the only torque developed at synchronous speed is the hysteresis torque. So in this diagram, hysteresis torque remains from starting to synchronous speed as a constant, that is called hysteresis operation range. So developed torque is practically constant from slip 1 to slip 0 or from starting to synchronous speed, and it remains constant at the synchronous speed. Torque speed characteristic. At synchronous speed, the induced torque in the hysteresis motor is proportional to the angle delta between the stator and rotor magnetic fields. An ideal torque speed characteristic is shown in the figure. The departure from the ideal characteristic 1 to 2 is due to harmonics present in the rotating field and other irregularities. So there, as seen in this figure, characteristic is curved near the synchronous speed and slightly the torque reduces because of the harmonics present in the rotating field produced by stator. Torque speed characteristic of a hysteresis motor is quite different from that of an induction motor. So this characteristic is different than the induction motor torque speed characteristic. Hysteresis motor performance. The torque developed by an induction motor becomes 0 at synchronous speed, while in an ideal hysteresis motor it is constant at all speeds from starting to synchronous speed. In a hysteresis motor, the locked rotor starting and pull-out torques are all equal. The hysteresis motor can pull into synchronism very smoothly even at high inertia loads. Advantages. Hysteresis motor has following advantages. There are no mechanical vibrations as the rotor has no teeth or slot or winding on the rotor. It can rotate high inertia loads. Multi-speed operation is possible using gear train or multiple pole windings. The operation is noiseless due to smooth cylindrical rotor shape. The speed and torque are constant. The motor is self-starting. It smoothly synchronizes. Motor takes constant current during starting and during its operation. It is very good characteristic as the starting current is constant. Disadvantages. Hysteresis motor has following problems. Its efficiency is low because of more losses, low torque, low power factor, high cost of rotor material. However, small amount of material is used, but still its cost is higher. Available in small size only. Poor power output. Its output is 25% of the output of an induction motor with same dimension. Applications. The hysteresis motor, due to its noiseless operation, is preferred for quality sound reproduction equipment like record players, tape recorders, sound recording instruments, electric clocks and other timing devices. Motor is made in small sizes and used in teleprinters also. Thank you.